Yes, sir. Thanks.
Yes, sir. Please, this is the time to start the session.
Yes, sir. Yes, sir. Good afternoon, sir. And good morning and good evening. First of all, I welcome the resource person, Dr. Ranjan Kumar Jana, and participants to the session on computing Basels and error function with the MATLAB basic, modified, and extended. So, Dr. Ranjan Kumar Jana is at SVNIT Surat since 7 December 2006. Prior to his joining IT, he also worked as lecturer at Nirma University, Ahmedabad, research fellow at Space Center, Ahmedabad 2004 to 6, and Vishwa Bharati Shanti 2003 to 4. Dr. Jana has been awarded Indo-US Research Fellowship for this year, for the year 2013 by IUSSTF New Delhi for postdoctoral studies at the University of Wisconsin at Urbana-Champaign, USA, and worked with the professor Bruce C. Brent. He has been awarded Research Associateship by Institute of Mathematical Sciences, Chennai from 1st of June 2015 to 31st May 2018. At SVNIT, his group is working on special functions, integral transform operations research, and data assimilation. He has published 50 research papers in national, international, of repute and conference proceedings, reviewed 49 papers. He has guided 6 students for PhD, 8 students are currently working towards PhD degree. 24 students completed their master dissertations. 15 students completed their summer internship under his able guidance. He completed 4 research projects, each sponsored by DST, CSIR, SBNIT, and SER. Currently, one project is ongoing, which is sponsored by ISRO. Dr. Jana has organized 14 national international conferences, 40 seminars, symposium, 11 workshops, 10 short-term training programs, 2 lecture series, 22 expert lectures at SVNIT. He has also visited different universities, George Washington Universities, Washington DC Universities of the Alliance at Urbana-Champaign, University of Wisconsin at Madison, Texas Tech University, University of Wisconsin at Eau Claire in USA, Ramangala University of Technology at Thailand, and University of Porto at Portugal at academic purpose. He has delivered 93 invited lecturers at different universities, institutions. He is member of American Mathematical Society, Society for the Industrial and Applied Mathematics, and life member of Indian Mathematical Society, Ramanujan Mathematical Society, Calcutta Mathematical Society, Society for Special Function and Application, Operational Research Society of India, etc. Now I invite Dr. R.K. Jana sir for his presentations. Sir, please.
Yeah. Am I audible to everyone?
Yes, sir.
Yeah, thank you very much, Srikantji, for introduction. Thank you. And first and foremost, I would like to thank the President of MathTech Foundation for this initiative to organize international training workshop on special function. and their application, computation of special function and their applications. Okay, we are in the verge of the exact middle. Okay, so far several session has been conducted. Okay, so basically I'll talk into two parts. First part I'll focus on Bessel function. Second part it will be error function. And lecture 1 I have entitled a title given as Bessel function and connection with Ramanujan's mathematics. So I'll discuss about basics of Bessel function, then how this Bessel function has connected with Ramanujan's mathematics, that we will discuss. After that, I will go for computation of Bessel and error function. Exactly whatever the title it is given, it was in MATLAB, but I want to compute here. Computation part is I have been focused, and my presentations will be Mathematica. You have already gone through MATLAB yesterday by Prashant Patel. Okay, and today as well for multi-leveler function presentation has been done by Dr. Meher Chandji. Okay, so I thought that it will be better if I'll tell about something about Mathematica. You know that computations part 2 we have the software MATLAB, Mathematica, and MAPL. Okay, so which are enormously used as a mathematical software in our daily use or bread and butter as a mathematician. So I'll emphasize how I'll demonstrate, especially two functions, Bessel and error function, in Mathematica, through Mathematica, that I will demonstrate here in the next 2 hours. Okay, so starting from my first talk, I'll go through like this. Is the title page is visible? PDF file?
Yes, sir. Yes, sir. It is fine.
So my first talk it will be Bessel function and connection with Ramanujan's mathematics. Okay, so this is my email ID. First one is personal email ID and the second one is the institute email ID. If you have any doubt, you can contact with my email ID. Okay, even through my web page also. Okay, if you go through SB90 website, you may get my web page also. So through that also you can go through. Okay, so in this present talk, in the present first talk, I'll discuss introduction to Bessel function. Then I'll go for generalization of Bessel function. Then integrals involving Bessel function, generalized Bessel matrix function. Then I'll go through the connection with Ramanujan's mathematics. So Bessel functions, it has been named after the astronomer F.W. Bessel. Okay, whose reign of the work is 1784 to 1846. You can see the picture of Bessel. So name has been given for the name of F.W. Bessel. And D. Bernoulli is generally credited with being the first to introduce the concept of Bessel function in 1732. So it is not like that, though the name is Bessel, but it was 1732. If you see, 1784 is the birth of Bessel, but it was started, Bessel functions has been, okay, generally credited with the Bessel functions by D. Bernoulli. And Bernoulli used the Bessel function of zero order. So we'll discuss today also J0AX, which is generally called the Bessel functions of order 0. So Bessel function has a order J0AX, JNX, like that. How it is coming, that also I will discuss. Okay, it has come as a solution of the problem of an oscillating chain suspended at one end. So if you have, if one chain is suspended at one end, then that vibrations or oscillations, it will give it, or it can be modeled as a Bessel's differential equations, and we will get the Bessel function as the solutions of the Bessel's differential equation. In 1764, Leonard Euler employed Bessel's functions of integer order. Okay, so first one is Bessel function of zeroth order. Now Bessel functions of integer order he has introduced in an analysis of vibration of a stretched membrane. So if you go consider about the more than one dimension, that time you will get membrane type thing. So that time to analysis the vibration of a stress membrane, he employed Bessel functions. Bessel, while receiving the named credit for these functions, did not incorporate them into his work until 1870. The Bessel function was the result of Bessel's study of a problem of Kepler for determining the motion of three bodies moving under mutual gravitation. So we have already heard about Kepler's problem. In 1824, he incorporated Bessel functions in a study of planetary perturbations, where the Bessel function in that case, we'll get the coefficients in a series expansion as the Bessel function. Okay. So that type of things also we can at the computation part, we'll discuss about how we'll get the Bessel functions as a series. The theory of Bessel function is also one type of special function, and the theory of height and differential function, which is also sometimes called special function in mathematical physics, it appears frequently in the solutions of differential equations. And the properties of special functions are numerous. They are expressible in terms of the differential equations they satisfy, the definite integrals over the products of these functions, the recurrence relations relating their various forms. So these are the importance of special functions. That's why they have several importance. And the Bessel functions are more frequently defined as solutions of the differential equation. So here, if you go through here, this is the differential equation of Bessel's. It is called also Bessel's differential equation. Since here B square is there, I'll get the solution as the JVZ, Bessel functions of order V. So if V equal to 0, I'll get J0Z as the solutions, 0th order Bessel function. Oh, same time it will be called the Bessel's differential equations. Okay, that is also Bessel's differential equations, and the order you will get by this Z square minus V square. So what type of solutions we will get? We will get two type of. This is a Bessel's differential equation. So the solutions we will get as the Bessel's function. One is called the Bessel function of the first kind, which is denoted as J, and it is of in Vth order, so JVZ. And another we will get as the Bessel function of second kind, which is called as the YVZ. So there is two notation. One is first kind, J, another is Y, which is Bessel function of the second kind. And if you go for the series solutions of this differential equation defined in one, you will get JVZ as this. So JVZ equal to nothing but summation of k equal to 0 to infinity minus 1 whole to the power k z by 2 whole to the power 2k plus b upon, okay, in the denominator gamma 1 plus b plus k factorial k. Here you can write also gamma k plus 1 also. Okay, so where mod z must be less than infinity, and not only that, argument of z must be less than of pi. So this is the series of JVZ, which is called the Bessel function of the first kind. And here JVZ is an analytic function for z belongs to C, except for a branch point at z equal to 0 when b is not an integer. When b is not an integer, that time we will get a branch point. And when v to be an integer, it is an entire function in z belongs to C. We know that what is entire function? Entire function is the functions where everywhere the function is analytic. Then I will focus into the generalization of Bessel functions, where we have several work also, that also I will demonstrate. Okay, so if you go through the generalization of Bessel functions, previous one is JVZ. Now, if one parameter has been introduced by right, EM right, we generalize Bessel function as this way. And the series also has been changed here. If you see here, previous one is changed here. This is there, but there is z by 2 whole to the power 2k plus b. Here I am getting minus 1 whole to the power k, z to the power k, gamma 1 plus b plus hk here. Previous one it was k, here hk. So this h has been come here and with multiplication of factorial k. And here h must be greater than 0, and the remaining it will be same, mod z must be less than infinity, argument of z less than 5. So this is one generalization of Bessel function which is introduced by Wright. myself, along with Salebhai and Professor A.K. Shukla, we have generalized right type of Bessel function, right Bessel functions or generalization of Bessel functions. Another way, we have used this way, MAJBZ, and we have defined by this way. So we have mix up both of the generalizations, the JBZ as well as the HJBZ introduced by Wright. So this is the another generalization, and we have deduced several properties of this function, and this is what for mod z less than infinity, argument z less than pi, and not only that. Yeah. M and B that must be belongs to C and there must be greater than 0. So this is the generalizations we have introduced and we have discussed several properties of that. And we have, so first we have discussed about some differential properties involving this generalized Bessel function. So this is the differential properties. What it is telling that for this condition, we can get ddz of, so derivative we can find in terms of this way. So this is the one differential properties. Another we can get this way for mod z less than infinity. I will get that this type of relations with respect to the derivative of that. Okay, so this type of relations already in JVZ also we can get J0Z. Similarly here also you will get this type of properties. Another property is there, ddz of z to the power 2m by h minus b mjbz can be written as this way, v minus 1 by m. So this is also another property for mod z less than infinity, argument z less than pi, and for these conditions we will get this also another relation. This is another relations like recurrence relation, though it is not like a v minus 1 or v plus 1, it is also v minus 1 by m. Okay, so this type of relations we have obtained for the generalized Bessel function. And if I go for putting particular type of value, then I can represent the generalized Bessel functions in terms of hypergeometric function, in terms of error function, in terms of several other known functions. So if I put this image like that, m equal to 2, h equal to 2, and p equal to 3 by 2, I'll get this hypergeometric functions 0f2 form. 0f2 here there is no argument, here is 2 argument, and with this is the parameter, this is the argument minus x square by 16. Similarly, if I put m equal to 2, h equal to 3, and v equal to half, I'll get 0f3. So this I can say that how we can relate Bessel function in terms of hypergeometric functions, that has been demonstrated. Now, if you put h equal to 1, m equal to 1, and v equal to half, you will get exactly root 2 by pi x sin x. Okay, so this is nothing but j half x actually, root 2 by pi x sin x. So h equal to 1, m equal to 1, we are getting exactly j half x. Then when I'll put minus 3 by 2, I'll get this minus root 2 by pi x, x sin x plus sin x. So for different value of h, m, and v, I'll get different type of Bessel function. So that's why the name is called the generalized Bessel function. Now I'll shift it integrals involving Bessel function. So we have proved certain results for integrals with Laguerre polynomials and Bessel functions also. So this is the Laguerre polynomial we have taken, and if we introduce this, I will get the result as this. So this is the integrals involving the Laguerre polynomials and Bessel functions, where theta equal to this type of parameter and phi is theta equal to this expression. Okay. And the 4-parameter Laguerre type polynomial is defined as this. So this is the 4-parameter Laguerre type polynomial, which is defined by this beta plus alpha. So this is the factorial notations we have used, and this is the gamma function like that. So this is this 4-parameter Laggard type polynomials. It is involving to deduce the integrals involving Bessel function. These are the relations when we will take alpha gamma belongs to C0, beta belongs to C minus 1. Beta belongs to C minus 1 means the real part of beta must be greater than minus 1. And if you put this one, we'll get actually 3 parameter. So if I have this one, this is 4 parameter, here it is 3 parameter, ln alpha beta x. So we have also deduced several corollaries from the theorem. If you see here, we have put like that for all z greater than 0, we have the known result like this. So this we have proved as a corollary also. Another corollary we have proved like this. For all z greater than 0 and beta mu belongs to C minus 1, we have this ln beta. Here also we have taken 2 parameters. Okay. So this is also 2-parameter Laggard type polynomial. So this is the integrals involving Bessel functions we have deduced as a result. Now we'll discuss about Bessel matrix function. Now orthogonal matrix polynomial is an emergent field in terms of theoretical and practical points of view. There are important connections between orthogonal matrix polynomials and matrix differential equations. The theory of special matrix function, this has become a vital research field in the study of statistics, probability theory, group representative theory, physics, engineering, and so on. So in 1994, Euler, they have introduced the Bessel matrix functions like that. So it seems like a Bessel functions, but it is, this M is matrix. So that's why we are getting as a Bessel matrix functions, which is defined by this. So taking that into consideration, and this representation of Bessel functions, we have introduced one generalized Bessel matrix functions, like in the next page. So we have considered the Galois Bessel functions and of these generalized Bessel functions. If you remember, we have used HMJVZ, here MJVZ. So in between this type of Bessel function is there, that is introduced by Galois in 2003, which representation is this one. Now, this is the motivations of introducing generalized Bessel matrix functions, which we have introduced like this. We define the generalized Bessel matrix function as this HJLZ, which is similar to the generalized Bessel function of Galois. So how we have defined? We have defined like this, summation k equal to 0 minus 1 whole to the power. So gamma inverse we have taken 1 by gamma L plus HK, so that we have written gamma inverse Z by 2, which can be written in the form of, so this representation can be represented in terms of hypergeometric matrix function form also, which is nothing but 0 with 1 H, which is written as this way, L plus 1 minus Z square by 4. So this is the hypergeometric matrix form. Okay. Is it okay to everyone? Hello? You getting the things what we are discussing?
Yes, we are getting you.
Yeah.
Thank you, sir.
Okay, okay. Now, so this where 0 of F1, if you see here in the previous, we have got 0 F1H multiplication with Z by 2 whole to the power L gamma inverse L plus I. Now, what is the 0 F1H? That is written in this form. This is nothing but gamma L plus I. So this is the matrix representation form of this hypergeometric matrix function. Okay. What about H and L? They are the matrices in C n by n satisfy the conditions. Real part of H must be greater than 0 for all eigenvalues. H belongs to sigma H. Ra must be greater than minus 1 for all eigenvalues. A belongs to sigma L. Also, Hk plus L plus I is a matrix in C n by n such that Hk plus L plus. So this type of, this is spelling mistake, inversible, not invertible. it is I, it will be in place of A. Inversible matrix for every integer k greater than equal to 0. So these conditions has to be satisfied for H, L, I, K like that. Then only I can represent the generalized Bessel matrix function. So in defining general Bessel matrix functions in terms of hypergeometric matrix functions, we need this type of condition. Now, whatever the Bessel functions we have introduced, consider that type of form also. If we consider, then we can extend a generalized Bessel matrix function as follows. Like we have used the AB notation, ABA. If you remember here, we have used H here, AM here, here V. Now we have changed the notation for matrix capital A, capital B, MZ. And we'll get this Z by 2 whole to the power M, 0, psi 1. So this is also another type of, this is also hypergeometric function. Matrix hypergeometric function. So there are also certain restrictions are there for ABM. ABM, AB and AM are matrices in C n by n, satisfy the conditions, real part of A greater than 0. For all eigenvalues, A belongs to sigma A. Rm must be greater than -1, Rb must be greater than -1. For all eigenvalues, A must belongs to sigma M, B belongs to sigma B respectively. Also, not only that, AK plus BM plus I is matrix in series such that AK plus BM plus I is an inversible matrix for every integer k greater than equal to 0. So these are the conditions to be satisfied such that I can write the extended generalized Bessel matrix function into this form. Now I can get the integral representation of also this Bessel matrix function. How it will be? For mod z less than infinity, argument of z less than pi, and n belongs to the extended generalized Bessel matrix function satisfying the following integral representation. So this extended generalized matrix function can be represented in terms of integral representations like this. So this is also I can write in the matrix form this way. So the proof we have not cited here. Okay. So these are the result we have deduced. So we have not yet written the proof here. Not only that, we can make the connections between this generalized Bessel matrix function with Laguerre polynomial like previous work, previous thing I have shown. Okay, for the generalized Bessel function. Similarly, for generalized Bessel matrix function also, we will get this type of relation. So this is the result we have got. Integrals involving Laguerre matrix polynomial. Okay, so here like that, what we got here? We got here the hypergeometric matrix function. Okay. Similarly, we can deduce the integral involving Jacobi matrix polynomial also. So Laguerre matrix polynomial. Okay. So we can use that Jacobi matrix polynomial also. So this is the result for real V greater than -1. B belongs to sigma A in terms of Campbell-Riffat function form like that. So this function is called also Campbell-Riffat function. So that form we will get here. So this is nothing but x square z square by 4. Here also z square x square by 4. Okay. So this has been due to the limitations of the space, it is not visible. Okay, so this is x square z square by 4. This is also z square x square by 4. Okay, so that had not been there. So this is the result we will get from the integrals involving Jacobi matrix polynomial with ABJ, JM. Now we will directly go to the. So where theta equal to this, delta ms. So this is the notation we have used to make the representation short. Then we can, this function again, I can write into the Srivastava and Daust function also holds true. Okay. So this also we can get it. Okay. So this is so how we can use this extended Bessel matrix function. So different result has been done by our group. So now I'll directly go to Bessel functions connections with Ramanujan's mathematics. So in approximately 1915, Ramanujan recorded two identities involving doubly infinite series of Bessel function. Okay. The identities are connected with classical and long-standing circle and divisor problem. I'll discuss this circle problems as well as divisor problems later on my presentation. So these identities are connected with the classical problem, which is called the circle and divisor problems. These results, which is stated in the entry 0.1 into 0.2 of the Ramanujan's lost notebook on page 335, he has cited the result, but he has not given the proof. So different groups, those who are working in hypergeometric functions, circle and divisor problem, they have tried to prove it. So here we'll give some proof, connected proof on this. Professor Band has done some work on that I will cite it here. Okay. The first identity involves the ordinary Bessel function J1Z. So we have known JVZ here. When v equal to 1, I'll get JVZ. The more general ordinary Bessel function JVZ is defined by 2. So I have already discussed this JVZ, from where it is coming, their differential equation, their series representations like that. So here, if I put v equal to 1, I'll get J1Z, and that has been given in the entry 1 or first identity. The second identity involves Bessel function of the second kind, Y1Z. Y1Z, I told that YVZ is another solution of the Bessel's differential equation. So YVZ is another solution. And not only that, YVZ and JVZ are related. What is the relations between them? This is the relations between them. How this Bessel function of the second kind is related with Bessel function of the first kind. YVZ is nothing but JVZ cos v pi minus J minus VZ. Another beauty of Bessel function is that J minus VZ is also defined. Okay, so JVZ cos v pi minus J minus VZ. So you can write JVZ cot v pi minus J minus VZ cosec v pi. So that way also you can write. Okay, so 24 is the relations between the Bessel function of the first kind and second kind, and both of them are the solution of the Bessel's differential equation. This is all about first identity. What about second identity? In second identity, that is another type of Bessel function is there, that is called the modified Bessel function. What is modified Bessel function? So this is modified Bessel function of order V. This is modified Bessel function of order 1, and which is defined by this way, KVZ equal to nothing but, that is also related with ordinary Bessel function of first kind, which is nothing but e to the power pi I v by 2, which can be written also cos pi v. Is it? So that type of things also here, minus e to the power minus pi I v by 2 jvij sin v pi. So this is the relations between the Bessel function of first kind with modified Bessel functions. So this is generally denoted as KVZ. So in the second entry, we will find Bessel functions. So both of the entry, it is directly connected with Bessel functions, which is indeed a very important study, and the proof yet it was not given. So several researchers has started working on that. Now, if v is an integer, then it is understood that we define the function by taking limits as v tends to n in 14 and 15. Now, whatever he has written the result in the right hand side, but he has not given the proof. Now, to how the proof is came, so to discuss that, Ramanujan may have, so to state Ramanujan's claims in the proof of the entry 1 and 2. So we need to next define a function which is nothing but fx equal to box x, that is the greatest integer less than or equal to x when x is not an integer, And if x is not an integer, that time I'll deduct x minus half. So half it will be deducted from x. That will give you the function. So one function has been defined, capital Fx, is like this, which is given in 26. So this is the entry 1. If you see here, this is the proof. So this is the series representation n equal to 1 to infinity fx by sin 2 pi n theta, which can be represented in terms of this pi x half minus theta minus 1 by cot theta, and here you will get the series of Bessel function here, summation n equal to 0 to infinity j1. So here j1 is involved here. Okay, j1 4 pi m n plus theta m n plus theta. And entry 2, what you will get? Sorry, entry 1 is this one, and entry 2 it is this one. So here fx is defined by this way, fx is defined in 26 like that. So if you will fx defined in this way, then that time you will get the relations between the series of the fx in terms of Bessel function. Okay, and what about I? I is related with y and k like this. So Barnett al. has proved 1790 entry 1 and 2 with different interpretation of the double series of Bessel function on the right hand side. In each case, they also observed that the Bessel function appearing 7 and 18 are mindful of classical circle and divisor problem. So how it is connected with circle and divisor problem, that I will discuss now. Now let R2n denote the number of representation of the positive integer n as a sum of 2 square. So this is denoting the number of representation of the positive integer n as a sum of 2 square. Okay, so how it is one number can be represented as sum of 2 square? The number different way of doing that is called R2n. Okay. Now, a representation with different signs and different orders in the summands are regarded as distinct representation. If I write 2 square plus 4 square, suppose it is 4 plus 16, 20. So 4 square plus 2 square also I will take as a different representation. So order of the summands also it is distinct representations. So this is the pictorial representation of the circle problem. And if you write this sum of them, you will get as pi x plus px. Px is the error term. The prime on the summation sign on the left hand side indicates that if x is an integer, only half R2x it will be taken counted. And the famous circle problem is to determine the order of magnitude of the. So the famous circle problem is to find pi x, it is okay, but px, finding px, it is called the circle problem when x tends to infinity. Had he given one approximation of px, that is represented in terms of Bessel functions. So that's why Bessel function is also connected with circles problem. If you remember here, this is almost up to here, it is same as the previous slide. This one. So px, the error term, has been provided by Hardy like this in terms of this summation n equal to 1 to infinity r to n. Here r to n, here r to n, x by n whole to the power half j1. So Bessel function also connected with circles problem. The forms of the Bessel function appearing in 21 and 17 strongly suggest that these two identities must be related. So there is a Bessel function and modified Bessel function can be represented also in terms of that. So that's why I can say that the two identities NT 0.1 and NT 0.2 must be related, and they also related with the Bessel functions as well. Then what about divisor problem? Let Dn denote the number of positive divisors of the positive integer n. So Dn is representing the number of positive divisors of the positive integer n. Here n is a positive integer and Dn representing the number of positive divisors of that number. Then I can write this way. Summation n less than equal to x, Dn can be written as x log x plus 2 gamma minus 1 plus 1 by 4 plus delta x. This gamma is called Euler constant, and delta x is the error term. Where gamma denotes the Euler constant, the prime on the summation sign indicates that if x is an integer, then only half dx is counted. And the famous this is also proposed by Dirichlet, so that's why sometimes it is called the Dirichlet divisor problem, that has been asked for the correct order of the magnitude of delta x as x tends to infinity. Previously, we are trying to find px, here we are finding delta x. So that is called the divisor problem. So this is the pictorial representation of the divisor problem. Divisors, so root x, 2 root x, y z equal to x. We are finding that type of things. Voronoi, he has established a representation for delta x. So previous one Hardy was given one px, approximation of px. Here delta x has been given by Voronoi in terms of this I1, 4 pi root x. So this is also giving one that suggested that divisor problem is also give it. So that's why I can say that the entry 0.2 is connected with divisor problem, and the entry 0.1 is connected with this circle problem. So this type of approximations we have used. The similarity of Bessel functions in 18 with those in 23 indicating that there must be a connection between these two formulas. Hardy related that Ramanujan had actually established a beautiful identity that included, as a special case, a key identity needed by Hardy for this proof, px equal to omega plus minus. There will be order of x to the power 1 by 4, where px is defined by 20. Ramanujan may have established entry 0.1 and 0.2 in order to attack the circle and divisor problem. However, we do not have any further work by Ramanujan in this direction. A proof of entry 0.1 can be found in 3 by Professor Bundt, and a proof of entry 0.2 with the order of summation on the right-hand side of 18 as prescribed by Ramanujan has never been given. So entry 0.2 proof is still pending. However, a proof of 18 with the order of summation reversed has been given in first work. I will give in the references. A Bessel function identity for the real sum, this an x minus n whole to the power q, is in fact equivalent to the functional equation involving gamma x of the corresponding Dirichlet series. In the study of the average order of an arithmetical function an, that is to say, in the study of n less than equal to x summation an, the aforementioned Bessel function identity plays a crucial role. Barn et al. Have established a real sum identity for this one, summation n less than equal to x minus a n whole to the power gamma minus 1, summation r by n, sine 2 pi r theta, which in the special case gamma equal to 1 reduces to 17. So this is also another way to prove has been presented. Barn et al. Also have established a similar identity for the real sum corresponding to 18. In each of these cases, a previously provided special case found in 6 played a necessary role. Now it is natural to ask if other classical real sum identities are associated with analog of entries 0.1 and 0.2. Again, Barn et al. Have found 3 additional results akin to the aforementioned entries. In each case, they have derived identities for certain real sums involving Bessel functions. However, the associated Dirichlet series satisfying functional equations with complicated gamma function factors, that is, they do not fall under the purview of the theorems in 6. So in conclusions, what we can say that the identities of entries 0.1 and 0.2, as well as further identities in the last notebook of Ramanujan, raise lots of interesting questions. So you can see what are the connections. That is connections with arithmetical numbers, circle and divisor problem, real sum. Okay, so which are indeed a further research study. So you can go through the Ramanujan's mathematics, you can go through the Ramanujan lost notebook where several identities are given without proof. So if you give the proof, then that will also be a part of research. So this is only 2 identities we have given, which is connected to the Bessel functions that I have given. And these are the reference of the work. Okay. So this is the Lida-Gallup paper in Generalization Integral Transform, which is appeared in 2003, like that. This is the last notebook of this. This is published in 1988. This is another. This is, we have extended general Bessel function. Thank you. Now I'll go for another talk. Okay. So I'll go for the second talk now. Is the screen visible now? Second talk, computation of Bessel and error function. Can anybody confirm? Hello. Can anybody confirm whether it is visible or not?
Yes, it is
Yeah,
visible.
it is visible. Please carry on, sir. Please carry on.
Yeah, okay. Now, whatever we have discussed, okay, whatever we have discussed, Bessel functions, I'll now go for computation of Bessel function. Then I'll go again some theoretical background of error function. Then I'll demonstrate with Mathematica. Now, again, second part, what I'll discuss? I'll discuss the computation of Bessel function. Prior to that, I'll go for little bit about Mathematica software. Okay, what is Mathematica? Mathematica is a system for doing mathematics by computer, such as modeling, simulation, visualization, documentation, etc. It is a commercial software and available on all computer clusters. It runs on most popular workstations, including Microsoft, Windows, macOS, okay, Linux, and other Unix-based system as well. It is used in all branches of engineering, biological sciences, computer science, statistics, number theory, discrete
Hello.
Here is no audio. Please check it.
Hello? Hello? Hello?
Yes, sir.
Is there any problem?
Hello.
Yes, sir.
It seems as if there's no one talking. We're not hearing anything.
No audio.
No audio, no video, no presentation.
No audio, no video, no presentation. I
presentation.
think this has lasted for like 10 minutes or so or more now.
Gandhi, session is over?
No, sir, I am waiting. There is no audio, no video.
Okay.
This is for 2 hour session.
Yes, yes. I just come back because I have to take tea. And just I come back, I see that there is nothing.
Okay.
Okay, just wait 1 minute. I am calling him.
So, yes, sir, sir. Please discuss to Rajan sir. Rajan sir.
Dear participant, please wait. Resource person disconnected due to network issue. He is rejoining the meeting very soon. He is trying to connect.
Okay, sir. Okay.
Yes. I request all the participant please be stay connected with us. Resource person is trying to reconnect again. Once again, I am requesting to all the participant due to network issue, resource person disconnected. Please wait for some time. He is trying to connect. There are many questions from the participant who are attending this session through the live streaming. Also, I am requesting to them also, please wait for some time. The session will re-continue.
On computing special functions. In previous lecture, we discussed about k gamma, k beta function, which are extensions of classical gamma and beta functions. In the present session, we do graphical and numerical interpretation of k-chamber symbols. All these three functions are very important. Write a program for computing k-level function and its graphical interpretation. So let's start step by step. First, I need to share my desktop with you. You can see this is the definition of chamber k symbol defined at this place. X belongs to C and K belongs to R and is natural number. Then X n K is equal to X plus K into X plus 2K and so on. This is the nth term. So to write the program for this function, how we can start? Syntax for the MATLAB will be in this way. First, we have to write the syntax and then we will use for our purpose. This is function. Then this is KP, just a symbol for the K poach symbol, and is equal to, we give the name K poach. And after that, see here how many parameters are involving in this function. X is variable, n is natural number, and K is parameter. So we have to pass all these three values through this function. So we have X, comma, N, comma, K. When to write the program, this function, and see here, when we have N equal to 1, in that case, we have X. This is the first product. But we have to start N equal to 1 and we need initial value. So to write the program for this chamber symbol, we have to consider first value when suppose that N is equal to 0, 0th term. Okay, so this is Kp is equal to 1. This is the initial value, and after that we have to apply for loop. So at this place we have R is equal to 1 and then N. So Kp will be equal to, this is the returning value of the chamber symbol, depend upon the value of N and value of X variable and value of K. So when we have N equal to 1, in that case, X1K will be equal to X. So this is the first value when N is equal to 1, and then we have N equal to 2 and so on. So Kp will be equal to Kp, we are using this initial value at its place, and then product, and use here dot star, dot product sign. This is X plus N minus 1. Then we have product K and suppress it. And after that, we will close the loop. And then after we have to close the function. So how this loop will work, it's also very important to understand here. Many times when we have to write the different type of problems, by using this pattern, it will help you. So initially when we have r is equal to 1, and when we put r is equal to 1 in this expression, this will be equal to x. And the value of this will we have equal to 1. And this is the returning value kp. So kp will be equal to we have x. Again, when we have n is equal to 2, suppose that n is equal to 2, then what will happen? The value of kp we have is x.
Oh, am I audible?
And then after when we put n is equal to 2 in this.
Hello.
Yes, sir, audible.
Are you able to see the screen?
Yes, the screen is visible.
Okay, so can anybody confirm where I was whenever I have stopped? Hello. Can anybody come?
Yes, sir,
Yeah.
you are audible and screen is fine.
Now I want to know where I was there when I was not knowing the particular time when I was out of the meeting. So can anybody confirm where I was there? I have completed the first talk, I think. I think I have started the second talk, then I have discussing Mathematica. That time maybe I was out of. Is it?
Yes, you were
Explaining about Mathematica.
introducing the
Yeah.
Mathematica, talking
Okay.
about Mathematica as a software tools. I think that's at that point you came offline.
Yeah, thank you, Oglev. Thank you very much for pointing at the proper time. I am very much sorry. I feel sorry that I was due to the network problem. I was out of the meeting. The rejoining was the problem actually. I could not rejoin again immediately. So it was taken time, 10 minutes. Okay. Thank you very much for your patience. Okay. So now I'll go for the next part of the talk. So this I have discussed. This is the persons who has been credited as the creator of Mathematica. Presently, we are in the version of 12.3.1, and the history of the revision you can find in this URL. Okay, and these are the work what can be done by Mathematica, standard arithmetic tool, which there has been several tool it has. Okay, so you can do the operations with integer, rational number, real and complex number. This is the part in which, in this international webinar or training workshop, we are discussing these things. Not only that, in special function also, I am chosen only two things, Bessel function and error functions, which I will demonstrate now using Mathematica. Apart from that, there are several built-in functions and constants, creating a few new functions you can do in Mathematica also. You can do the factorizations, you can find the polynomials, representation of polynomials also, simplification of polynomials, reduction, solution of simultaneous linear equations, vector operations, matrix and tensor operations also you can do, sum and products also. You can do the plot also, 2D plot, 3D plot, contour plot, density, parametric plot, list plots, animations. You can do the operations on calculus like limit, differentiation and integration, Taylor series, solving ODE, PDE also can be done using Mathematica. Then finding the roots, numerical integration, curve fitting, that can also be done. Now coming to the things. So to represent Bessel functions, where we are generally denoted by like JVZ, if you remember, in my slide presentation, JVZ I have used. So same way in the mathematical notations, we will use like J and K. Okay, n is the order of the Bessel function, K is the argument. So we can go for different order Bessel function as well as different point the value of the Bessel functions also. So here I have demonstrated one. If I take the 5 by 2, 5 by 2 is the order of the 5 by 2. So if I go for 1/2, what I'll get this as the expression. So j half x, it is the same series form of like root 2 by pi sine x by root x. Okay, j minus half also you can go for. What will get? You will get root 2 by pi cos x by root x. So you will get j half z plus j minus half z. That type of form you can get it also. You can write in terms of exponential notation also. So that type of things you can go for. You can find not only half minus half, you can go for 3 by 2 also. Like that, just to change this. What you will get? You will get this type of root 2 by pi minus cos x plus sin x by this one. You can plot that one also. So that can be plotted like this. Here it is minus 30 to 7. You can go for minus 0 to 37 also. So this is the plot in 0 to 7, 37. Okay, you can make it bigger also, like doing this. Sorry. Okay, so this way we can find different types. So if I go for 5 by 2, then again I will get the things like that. This is the, again I can plot that one also. So again I can. So this type of computation of Bessel functions, you can get it. 0 to 37, you can reduce it also so that I can visualize in better way. So this type of things you can go for. So 0 to 10, you will get minimum numbers of root. So we can go for extend like that. I can go for 40, suppose. So this type of number of roots, you can go for 100. This type of you can representations, you can elongate that also. So very easy, you can do it. Okay, now if I want to go for zeroth order Bessel function, I am changing the value of this, like zeroth order Bessel functions, but k value I am changing, the argument value I have changed. So I will get different type. This is exactly by J0 you can find value. So if I write 1, I'll get the value J01. So J01, I'll get it. 1.2, I'll get the numerical value. 0.6. Okay. Now, if I want to go for different type of value, so 3.2, you will get the value 5 Bessel's order. Fifth order at 3.2. So different order at the same point, you will get this way. This is the value you will get. So here, different order at the same point, I will get different value. Now, if I want to find J0x, plot J0x from minus 5 to 5, I'll get this. Okay, J05 minus 5 to 5. If I go for minus 37 to 37, this way you will get. So if you elongate, you can more number of crossing with the x-axis like that. More number of roots are there. 1 minus x square by 4 x to the power 5, 4 by 64 minus x to the power 6 by 2304, like that. Okay, so you will get it. If I write 4, I will get up to here. If I write 5, then I will get only this much. Because up to 5 is 0th coefficient, so plus order of x to the power 6. This is infinite series, so all the term it will be x to the power 6 and more than that. Now, 0 of Bessel functions also you can find. You can find j and k at the value of different points. So I'll get this. So here I'll get I can form the table of Bessel functions also like this. Okay, so this way we can find different order Bessel functions also at different point. I can make a table. Similarly, we can discuss about the orthogonality of Bessel functions by this graph, where J0 alpha x has been represented by this, J0 beta x, J0 gamma x, and we have given the value of alpha, beta, gamma also, which is alpha equal to this, J01, J02, J03. That is the case, this value. So that way you can plot it different value. So this is, then we can go for next kind also, second kind, which is denoted as YNK or YVZ, which I have used as an expression. So what it is nothing but Bessel YX series, you will get gamma function, Euler gamma function up to by log x this. So this is represented in terms of this way. So this is the representations. So if we go for Bessel y half x also, we will get minus root 2 by cos x by root x. J half x, we got what? Root 2 by sin x by root x. Here we are getting Bessel function of second kind as this one. So that's why we can say that there is a relation between JVZ and YVZ. Similarly to the JVZ, we can plot Bessel function of second kind also, y0x, y1x, y2x, y3x from 0 to 10, from minus 10 to 10 also you can go for. There is no part, so I can go for, so we'll elongate like that, 0 to 10. Okay, so this is all about function of second kind. So you can go for real part, imaginary plot, real and imaginary plot, complex plot, or Bessel function of second kind. So this can be used as the solutions of the differential equation also. So you can see here we have representing the solutions. So this is Bessel's differential equation, x square d2 by dx2 plus x d by dx plus x square minus n square. So I can write x minus n into x plus n. So this is equal to 0, yx. And I want what I will get? I'll get this Bessel function.
Sir, again, your voice is breaking.
No, I shall.
The video is hanging as well. No voice down. The video is also hanging.
Yeah.
Yes, yes, the presenter voice audio
Yes,
is
it
no
may
longer
be due to
coming up.
yes, please. It may be due to the low network because network issue is there. Please wait.
It's all right.
Dear participant, please stay connected with us. This is the network issue. Resource person will reconnect again. He is trying to connect. Dear participant, please stay connected and wait for some time. Speaker is trying to resolve the problem.
Yes, sir. Question so far. E squared over 2.
Again, voice is missing. Now it's time to conclude this session.
Sir, we should wait for a few minutes.
Okay.
Guys, we will conclude the session.
Okay. Okay. Sir.
Yeah, we understand this is a network issue and it may happen anywhere.
Yes, sir. Sure. It is a technical issue.
Yes.
We never deny.
Yeah.
And from the
Our speaker has joined the meeting. He is trying to share the content. Not yet, sir. Your content are in the process of sharing, but not shared yet. And voice is still breaking. Dear participant, I got the message from the speaker. There is a very big problem for due to network problem and a technical issue is there. Now I request to the moderator, please conclude the session.
Thank you, sir. There is a very big problem, big issue in network. So, sir has discussed in two topics in lecture one, Bessel functions and connections with Ramanujan mathematics. And lecture number 2, computation of
Shrikantji, please excuse me. Our speaker is there. He is connected now. Sir, you can unmute.
Yeah. Now I can mute. Yeah, sorry for the disturbance due where my hand is not there actually. Network as well as the power outrage there. I have tried in my mobile also, but it was sometime I could not unmute myself. Sometime the video is lagging. Even Merji also told that my voice is also lagging due to the network issue actually. So LAN network is not working due to the power outrage actually here in the department. There are several construction activities going on in our institute. Maybe due to that. And sorry for the interruption. Okay, so I have left with error function thing. Okay, so it will not an issue if anybody interested. I'll upload the error function thing also such a way that you can go through. Okay, so whatever the presentations I have made, that may be available to all the participants. You can go through that. You will get the idea. It is not like that. You will get from the content also. Okay, just play with what you have to do. You have to download Mathematica. The trial version itself it will work, and you play with the things such that you will know the Bessel function properties, error function properties also. Okay, if you give several different value of the argument, you will get different type of functions. The zero is there, how orthogonality, how I can approximate error functions. So that demonstration has been done there. So you just go through. I'll upload that things in the maybe tomorrow or day after tomorrow, such that you will get the content. And I am urging you to go through this content such that you will get the idea. Okay. Yeah.
Thank you, sir. So I thank you very much for your presentation. The participants also learned and will ask you by mail or other if you receive after your content. And if you have participants, you have any question, you can write about the Bessel's functions like.
And you can directly, if I am audible, you can directly ask me also if you have any doubt related to the presentation.
About Bessel functions, orthogonality, applications, error functions. Okay, no questions. So I again thank you, sir.
Thank you, Sikanji.
Okay, and participants for making it very lovely sessions. So thank you, sir. I hope we will meet you again soon.
Yeah, thank you very much. Yeah, so participant, if you have any query, anything, you can directly write to me through mail. Okay, so I'll try to reply. Okay, so again, sorry for the interruptions. Okay, so I could not fluently make it convenient to present the content properly. Okay, thank you very much. Thank you, Meherji.
Thank you, dear Professor.
you,
The content
Dr.
which you present are really very informative, very valuable for all the participants. Yes, we always have some time technical issue, but this is a part of no problem, sir. But the content really very informative, very valuable, and I think the content will be very helpful to all the participants. And also we will try to share with all the participants the content which are presented in this session. And also we regret the technical issue which we face, the problem. And I hope in the coming session will be very smooth. Some are not in our control. Thank you all the participants, and thank you, dear Professor, once again for your valuable time and the content which you present here.
Thank you. Thank you very much. We'll meet you tomorrow again. Thank you.
Thank you, all of you. We will resume the meeting tomorrow at the same time, 11:30, and the meeting link will remain same.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you. Thank you, everyone.
Thank you. Thank you. We're grateful.